Hello. So this will just be a continuation of the last stream. You'll notice I've skipped a few chapters in the book. I went from 1 to 5. That's just because I kind of wanted to get to the interesting stuff, and I was feeling kind of impatient. This will be about limits. Basically, the epsilon-delta definition in particular. I just want to go through one of the main theorems covered in Spivak, which goes through the uniqueness of a limit, and then go through several of the problems, emphasizing the techniques and lots of examples. So without further ado, I gotta plug in my drawing tablet. One sec. Of course, I put the USB the wrong way. Okay. So limits. So the idea of a limit is like very intuitive. We represent functions by these curves in the plane. And let's say this is a point A, and it may or may not be defined at A. It may be defined but not actually equal this value to which it seems to approach. But regardless, it's possible to define the limit whether it's defined or not, or even if it is defined and it's kind of sticking up here like this, the value. So intuitively, let me just go full screen. I call my function f of x. So intuitively, the limit as x goes to a of f of x, and let's call this through this y value L, is equal to L if as x gets close to a, f of x gets close to L. I mean, that's just really obvious, but in analysis, we want to make everything precise, and this whole notion of gets close is kind of murky. I mean, how close do they need to be? I mean, that will depend on the problem, but basically what we're trying to convey with this is that if we allow a certain amount of error in how close f of x becomes to the limit to which we are claiming it's going to approach, then there needs to be a corresponding error related to this original, the error in f of x, a corresponding error for the independent variable x relative to the input value a, which sort of determines how close x needs to be to a in order for f of x to be within the original error of L. So this idea of gets close to, it's not really an absolute notion of what this means. It just has to be interpreted in stages. So the rigorous definition of the limit is as follows. So limit as x goes to a of f of x is equal to L if for all epsilon bigger than 0, there exists delta bigger than 0 such that f of x minus L is less than epsilon whenever x minus a is less than delta. And we also put the 0 less than on the left here. Of course, absolute value is always non-negative. So all this 0 less than piece is doing is ensuring that absolute value of x minus a is not actually equal to 0. This is important because when we talk about limits, x does not actually have to equal the input value a, as you can see in our example here. If we allowed x to be equal to a, then the value of f of x could end up well outside a sufficiently small error, which is placed about L, right? But the idea of the limit is sort of stable under changing this value at the point at which we approach. So we don't really care the value that it takes or whether it takes any value at all at this point. It's just what's happening nearby, which is important. The other thing too, so epsilon is this error for f of x, which I was talking about, and the statement gets close for each of these variables is conveyed by these two inequalities. So the closeness of f of x to L is determined by epsilon, and the closeness of x to a is determined by delta. So the idea is that for a given error, which is it could be arbitrary, an epsilon, within which we want to have f of x an error of f of x lying within that error of L. We need to be able to figure out a corresponding error for the independent variable x, such that if x lies within that error of a, then the f of x will lie within epsilon of L. So this is a precise expression of the idea that f of x gets close to L as x gets close to a. F of x can be made as close as we like to L, provided we only make x sufficiently close to a. So having a definition is one thing, but knowing how to use it is quite another. It's kind of like knowing the rules of chess versus knowing actually how to play. So it's two totally different ball games. But before I go through any examples, just want to go through a quick proof that actually it highlights some really useful techniques which are used time and time again in analysis. Namely the triangle inequality and the trick of adding and subtracting the same thing, which, okay, I mean, you'll see it in action, but I just want to mention that beforehand. So yeah, before I get to the problems and examples, let me just prove this theorem. So the theorem is that limits are unique. More precisely, if the limit of f of x as x approaches a is equal to L, and the limit of f of x as x approaches a is equal to m, for example, for whatever, and m is not necessarily equal to L. They're not equal a priori. However, if they are both equal, if the limit of f of x as x goes to a exists, and L and m are two potentially or possibly different values for this limit, they actually must be the same. Okay, this seems so obvious as not even to deserve mention, but we do actually need to show it because the intuitive idea of limit has been replaced by a rigorous definition, and even if intuitively it feels like, I mean, a function, if it's getting really close to something as x approaches a, it can't be getting close to something else. That makes perfect sense. But that's not the same as a rigorous proof, because our definition actually encompasses a much larger class of situations than our intuition would normally be able to handle. And until we actually prove this, there's no way to know whether or not there's an example which would kind of break our intuition. There's lots of instances in math where there's perfectly obvious sounding things that turn out to be false. So we need to be very careful about this kind of stuff. And it does turn out, actually, there are certain situations where limits aren't unique. There's the field of topology, where you can define limits in a much more general sense. And the key property of a space that a space must have in order that limits be unique is that it's Hausdorff. The meaning of that is that different points can sort of be localized and separated away from each other. But there exist spaces which don't have that property, and they kind of come up naturally in some areas. And for spaces like that, there would not be a notion of unique limit. So, yeah, this does come up sometimes. Anyway, so for the proof of this, so a really useful trick in analysis, if we want to show two things are equal, it's enough to show that the absolute value of their difference can be made smaller than any positive number whatsoever. So it's helpful when you want to show two things are equal, not necessarily going to work all the time, but oftentimes you can analyze the absolute value of the difference of the two things and determine whether or not that can be made smaller than any positive number. Okay, so that will turn out to be very helpful in this situation. Another trick, which is used time and time again in analysis, is to add and subtract the same quantity. And this is going to seem a little strange at first, but just bear with me. So if I were to add and subtract f of x in the, sorry, that should be an m, not an l. Add and subtract f of x in the middle here. I now want to use a third technique, which is just ubiquitous in analysis, and that's the triangle inequality. So if we group the first pair of terms and the second pair of terms together, we can bound this expression above by this sum. Absolute value of L minus f of x plus absolute value of f of x minus m. And then finally, I can switch the order of these terms in the first absolute value, because that's the same as multiplying by a negative, but that doesn't change the absolute value. Okay, why do I want to write it in terms of these two expressions, this guy and this guy? Well, that's because we know how to control those. Those are precisely the expressions which occur in the definition of the limit. If we were to translate these two statements in terms of the rigorous definition here, we know that we can make both of those expressions very small, provided x is sufficiently close to a. All right, let's work that out rigorously. If if we let epsilon be bigger than 0, then there exists a delta 1 such that 0 less than x minus a less than delta 1 implies f of x minus L is less than, say, epsilon over 2. Because remember, I mean, I could have just said from the outset, let epsilon over 2 be the small number, the error for f of x. But, well, you'll see why I'm picking it to be that in a moment. And there exists delta 2. There exists delta 2 such that 0 less than x minus a less than delta 2. By the way, these are both bigger than 0. So this implies then that f of x minus m less than epsilon over 2. All right. Now, let's set delta equal to the minimum of delta 1 and delta 2. Then, if x is within delta of a, both of these expressions will have to be less than epsilon over 2. You can probably see where this is going. So now if I go back up to my L minus m and look at this line, we're actually adding those expressions, but each of those is less than epsilon over 2, provided I make x within delta of a. And so, let me just write that. So it's less than epsilon over 2 plus epsilon over 2, which is epsilon, provided 0 less than x minus a less than delta. All right. But if you go all the way back to the left, L minus m, there's no x appearing there. X was just kind of, it was used as an auxiliary, like, intermediate step. And so, I mean, like, this middle part will only be true for certain restricted values of x. But the L minus m, I mean, this is independent of x, and we've just shown that that's less than epsilon. So the upshot of all this is that absolute value of L minus m is less than epsilon for any epsilon bigger than 0. Well, it's an absolute value, so it's also going to be non-negative. This actually implies that it is equal to 0. And of course, that means that L and M are equal. The reason it must be equal to 0 is if L and M were not equal, then you would have only to take epsilon to be something smaller than the absolute value of L minus M, and that would give you a contradiction. So the only number which is non-negative and smaller than any positive number is 0. Yeah. So it's a really useful trick. Sometimes you don't quite have to show something 0 directly. You can just show it has to be smaller than an arbitrarily small thing. Okay. That completes the proof of the uniqueness of limits. There's all kinds of these, or there's these limit laws, which facilitate the calculation of limits quite a lot. So the limit of a sum is the sum of the limits, and limit of a product is the product of the limits. There's no weirdness with the rules as there is for derivatives. It's all what you would intuitively expect. The proofs are just kind of technical, and I won't really go through them, I don't think. But the important thing is to know how to use them. All right, so this brings us to the problems. Yeah, I'll start with problem 1. So this first set of problems is just basically calculating a bunch of limits. All right. So the very first thing that you always want to do when trying to work out a limit is see if it's permissible to just plug the value in. What I mean by this, well, okay, I guess I haven't talked about continuous functions yet, so maybe let me just do this step by step, actually. So we're not going to use the epsilon-delta definition for this. There are some future examples coming up for which it will be used, but for this example, not going to do that. So there's a couple ways you could proceed. One way is to take the limit into the top and bottom. I'm going to suppress the subscript in the limit. We'll just have to remember x is approaching 1. And now we can work out both of these limits separately. So you have to be very careful as well if you take a limit into a denominator. By the way, before I even do this step, like before I even go from or write this equal sign, I have to check that both the limits of the top and bottom exist, and also that this bottom one is non-zero in order to even write this. But thankfully we're in luck because that bottom limit is actually 2, and this top limit is 0. It's just 1 squared minus 1. Alternatively, you can simplify the expression inside a little bit. So this is actually just limit of x plus 1, x minus 1 over x plus 1, which comes out to the limit of x minus 1. And all of this is just algebra, so like it leaves the value of the limit unchanged, because as far, I mean, it's the exact same function, as long as x is not like -1 or something, but we're approaching 1, so it's fine. And of course, that's going to be 0. Sorry, this is part 1 of this problem. All right, I'm going to go actually skip ahead to problem 2. So let's look at part 1. So 1 minus root x over 1 minus x, and x is approaching 1. So now it is actually not valid to just pull this in the top and the bottom, even though the limits of the top and bottom exist at 1. The reason it's not valid is because this limit is 0, so this is bad. However, that doesn't mean that the total limit does not exist, because there could be some cancellation, and it happens that there is in this case. So we have to do a bit of algebraic manipulation before we can actually plug in any numbers. The usual trick when dealing with radicals is to multiply by the conjugate. So if I take, again, I'm going to suppress the subscript for the limit. So if I take the expression here, the conjugate is just for the square root expression. So if you have a plus b square root of q or something, the conjugate is just a minus b square root of q. So you just take the negative of the square root part, or flip the sign of the square root part. The reason this is a useful thing to do is because of the difference of squares formula. So, oh, by the way, we can't just multiply by that, we have to divide it as well. Otherwise, we'd be changing the expression. So this is kind of a complicated looking way of just multiplying by 1, but it's useful because the top expression is going to simplify quite a lot. So we're going to have the limit, and now we have 1 minus root x times 1 plus root x, which is 1 squared minus root x squared, or 1 minus x, but I'll write that later. And now this bottom turns into this. And we get 1 minus x on the top over 1 minus x, 1 plus root x. Those will cancel. And we have a limit of 1 over 1 plus root x. Okay, so what does this do? Now we actually can take the limit to the top and the bottom. Notice we haven't actually changed our expression. I mean, we've we have made it look a little different, but it takes on exactly the same x values for all x not equal to 1 at least. And so it must have the same limit, since as far as the limit is concerned, we only care about the x values nearby 1, not necessarily actually equal to 1. And the limit of this is the limit of 1 over the limit of 1 plus root x. X goes to 1. And as x goes to 1 at the bottom, it's just 1 over 1 plus 1. Or sorry, 1 plus root 1, but that's just 1 plus 1, so it's fine. And we get 1/2. All right. All right, let's do one with the epsilon-delta definition. So this one looks kind of complicated. But it's not too bad. Okay, find all right, so this problem asks us to find the limit of f of x as x approaches a. Here, a is going to be 0. And we need to prove that the limit is equal to that value using the definition, the rigorous definition. Okay. Right, so a guess. Here, I'll call this thing L, little l. So the guess is that at a equals 0, the limit is going to be 0, just by plugging in 0. This when we define continuity, we'll see that this is a continuous function, and so the limit of this function is just the value it takes on at the value a. So the guess is that L equals 0. Okay. So the proof, well, we're going to have to let epsilon be bigger than 0. We want to show, we want to find a delta bigger than 0 such that if x minus 0 is less than delta, then f of x minus 0 is less than epsilon. And delta is going to depend on epsilon. All right, so let me just split this into two parts. This is going to be kind of scratch work. And I want to start with my f of x minus 0 part. So I want to just look at this expression. And we want to write it somehow in terms of this. That's because the f of x minus 0 is what we want to be able to control. And the absolute value of x minus 0 is what we have control over, because we are free to choose the delta as we please. So if I can bound the former thing by the x minus 0 somehow, something in terms of it at least, in a simpler way, then that will give us a clue as to how to choose delta. It'll make more sense when you see how it goes in practice. So we have this. Okay, so absolute value of x, 3 minus cosine of x squared. That's f of x minus 0 in absolute value. We want to make this small. So the goal is to try and bound it above by something which is simpler, which is easier to work with. Before I bound it above, though, I want to just move the absolute value into both of these parts. So absolute value of x times absolute value of 3 minus cosine of x squared. And now I would like to bound it above by something simpler. In particular, something in terms of absolute value of x, which is the thing we are able to control via delta. That's the idea here. So we have an absolute value of x right here. There's just this annoying 3 minus cosine of x squared factor that is getting in our way. So it would be very nice if we could just get rid of that somehow. Unfortunately, we can't just delete it. But it doesn't turn out to be a huge issue because that term is bounded. In particular, we can actually use the triangle inequality to write that term in this way. And then this piece is actually bounded above by 1 because the cosine function is bounded in absolute value by 1. Of course, absolute value of 3 is just equal to 3. That's less than or equal to 1. So in total, we get absolute value of x times 3 plus 1, or just 4 times absolute value of x. Okay, so what we started with was the thing which we wanted to make smaller than epsilon, and now we have bounded it above by a relatively simple expression in terms of the thing over which we have complete control, which is absolute value of x. So now the question is, what would a suitable value of delta be? An error for the x variable, which would bound our f of x, our error of f of x from 0 by epsilon. Well, this will be less than epsilon, provided absolute value of x is less than epsilon over 4. So we want to set delta equal to epsilon over 4. Now if I go to the left side, here's how we would actually write the proof. I know I said let epsilon be bigger than 0 already, but I'll just reiterate. So then we want to set delta equal to epsilon over 4. Then if 0 is less than absolute value of x and less than delta, we get this. So now with this, you can actually just follow all the steps we have here if you wanted to fill them in. I'll just skip right to the end because we already know how to do all that. And now we use the fact that absolute value of x is less than delta. So 4 absolute value of x is less than 4 delta, but delta equals epsilon over 4. And then we're done. Okay, so that's the proof of that. So let's look at part 2. X equals x squared plus 5x minus 2, and the a value is 2. So our guess is that the limit of f of x as x approaches a, well, that should be 2 squared plus 5 times 2 minus 2. So 4 plus 10 minus 2, which is 12. All right. Okay, so let epsilon be bigger than 0. We want to find delta such that x minus 2 less than delta implies f of x minus 12 less than epsilon. All right, so just as before, I'll set aside a little section for scratch work, and we will put the formal proof on the left. Once again, we're going to start with the expression over which we want to have control. Right, like f of x minus 12, as yet we do not know that that can be made as small as desired. What we do have control over is this absolute value of x minus 2. So we want to write the f of x minus 12 somehow in terms of absolute value of x minus 2. At least we want to bound it above by something, which can be expressed in terms of absolute value of x minus 2. Yeah, the basic philosophy is just that you take the thing over which you want to have control and bound it above by the thing over which you do have control. And then you can kind of adjust the parameter delta as you need once you have simplified it to sufficiently. Yeah, we'll look at f of x minus 12 here. So we get x squared plus 5x minus 2 minus 12. Okay. We get x squared plus 5x minus 14. All right, so now this kind of looks complicated. It's not entirely obvious where to go from here, but the guiding factor, the guiding clue is we don't really have control over just x itself, but we do understand x minus 2. That's something which we are able to make very small. So if we can reframe this expression in terms of x minus 2 somehow, that will be ideal. So in order to do that, we can use the same trick of just adding and subtracting. I hope I don't make a mistake here, but we should get some nice cancellation if I do this correctly. we get x minus 2 squared plus 4x minus 2 plus 4 plus 5x minus 2 plus 10 minus 14. Okay, good. So the constants are going to cancel off perfectly. That's what you should expect. The expression here should vanish at x equals 2. Otherwise, it's not going to get small, which it needs to, or for this to work. Okay, so then, right, we get x minus 2 squared plus 9 times x minus 2. And now it's very tempting to just factor out x minus 2, so that's what we will do. Sorry, and I will also put the absolute values over both factors. So pull out x minus 2, and we also get x minus 2 plus 9, which, okay, I'll just write another line. It's x minus 2, and then x plus 7. All right. Right. So the thing is, the x minus 2 we understand, we have control over. This is something we are able to make very small. It's just that x plus 7, whereas before we had just a nice constant times the absolute value of x, now we have another function of x times the absolute value of x minus 2 now. But the point is, we're not allowed to just be like, oh, well, like set this less than equal to x plus 7 times delta, and then that's equal to epsilon, so delta equals epsilon over absolute value of x plus 7. Doesn't work because delta is not allowed to depend on x. That wouldn't really make sense because, like, delta is the error for x that's been chosen, and it can't really allow it. You can't allow it to change as x is changing. It would sort of defeat the purpose. So we need to do a little more work. Now this absolute value of x plus 7, intuitively, what is this going to be near? Well, if x is close to 2, one would think the absolute value of x plus 7 is going to be close to 9. So it shouldn't be too hard to find a decent upper bound for this, just a constant. It's the important thing is that it's not going to blow up or anything like that. But in order to do this rigorously, so we're going to actually impose a constraint on delta. So suppose delta is less than 1. Or less than or equal to 1. Alright, so then the absolute value of x minus 2 is going to be smaller than 1. And in particular, so this means minus 1 less than x minus 2 less than 1. To get an x plus 7 here, I just add 9 to both sides, so plus 9 plus, add 9 to all three parts. That gives you 8, x plus 7, and 10. And now, so for this constraint on delta, that delta be no greater than 1, we actually have that x plus 7 must be strictly positive. So we're free to put the absolute value bars back around it because it's already a positive number for this range of delta. And we don't really care about the 8 part, but we do care about this 10. That's absolute value x plus 7 is less than 10. So provided we make delta small enough, we can simplify this. And that's fine because delta is entirely under our control. So we're free to make it smaller if it makes things simpler. We will, of course, have to incorporate that into our final solution. So delta is going to be a function of epsilon. It's going to have to be like the minimum of whatever function of epsilon we find, and also 1. So it's going to have to involve both of those. But anyway, this is going to be less than x plus 2, x minus 2. X minus 2 times 10. And that's going to be less than epsilon, provided provided delta equals epsilon over 10. Or, okay, maybe I should write one more step. Provided x minus 2 is less than epsilon over 10, so take delta to be less than or equal to epsilon over 10. All right, so in total, our final delta, this should actually be the minimum of these two things. Since it's got to be no larger than either of those, if you take it to be equal to the minimum, then both the conditions which are required to hold will be satisfied, and the proof will go through just fine. It's a little ugly, but it gets the job done. That's the idea. So now for the rigorous proof. So we'll let epsilon be bigger than 0. We're going to take delta kind of mysteriously, if you didn't know anything about our scratch work, to be equal to the minimum of 1 and epsilon over 10. And then you can follow our inequalities, which we went through here. Everything up to this part follows through just regardless of any assumptions on delta. But to go from here to here, so this is where we require delta less than or equal to 1, and finally to go here, epsilon, we require delta less than or equal to epsilon over 10. So in order to put the last couple steps on the chain of inequalities, we need both of these conditions on the delta. Oh, sorry. I also forgot to mention if 0 is less than x minus 2 less than delta, okay. All right, let's skip ahead to problem number 8. See what time it is. Oh, it's 8:30. So I'm going to take a little bit of a breather. Let's see if I can watch this on my phone right now. Breather. Oh, cool. Let's see if I can watch this on my phone right now. Breather. Oh, cool. Let's see if I can watch this on my phone. Okay. So problem 8. It's kind of asking these counterexample style questions. So if limit of f of x and the limit of g of x do not exist, can the limit of the sum exist? All right. So the answer to these kinds of questions is, well, I mean, it depends, but in this case, yeah. So it's possible to add two functions which are very badly behaved and get something really simple. In fact, we can find an example or two examples of functions which don't have a limit anywhere, but which add to 0. But I mean, basically, yeah, you get these kind of trivial examples where, like, you find one function that looks really bad, and then you take its negative, and it's got like the same bad properties, and then you add them together, and you just get like 0, the simplest function ever to exist. And then, of course, you can ask the same question. Okay, well, just let me go through the example. This is an important example, actually. So let's set f of x to be equal to 1 when x is rational, and then 0 when x is irrational. I guess it doesn't matter which ones get sent to 1 or 0. Anyway, if we go g of x equals negative f of x, okay, so the claim is that the limit of f of x as x approaches a does not exist for any a. Intuitively, the reason for this is because as you move closer and closer to a, whether a is rational or irrational, there are infinitely many numbers of both types which occur infinitely often as you get closer and closer to a. There's never any point past which any point of approach to a past which you stop encountering rationals or stop encountering irrationals. Another way of, this is a consequence of the property which these two sets share, that they're dense in the real line. between any two real numbers, you can find a rational number as well as an irrational number. It's just not equal to either of the two original numbers. I don't think I want to go through the rigorous proof of this right now. It's let me see. Yeah, but obviously f of x plus g of x is equal to 0. That's the important thing. And 0 is very well behaved. It's got limits at every value, for every value of x. Okay, so same question for probably shouldn't use q because that's already representing rational numbers. Same question for f of x times g of x. So in other words, if we have the same hypotheses, limit of f of x, limit of g of x both exist, does the limit of the product exist? Question mark. Or a better way of saying it is, can it exist? And right, this I should have mentioned at the start. So we know when each of the limits separately does exist, that the limit of the sum will exist. We have a sufficient condition for the limit of the sum to exist. But what this example is showing is that this sufficient condition is not actually necessary. So it's possible that the limit of a sum will exist, but the limits of the component parts do not exist. All right. In fact, it's really important that, well, at least for the sum, that both of these fail to exist in order for the sum to exist. We'll get to that later. Sorry. But as far as the product is concerned, okay, well, we'll start with the same function, our Dirichlet function. I can't remember if the Dirichlet function is ones on the rationals or the irrationals, but it's a variant of the Dirichlet function. Anyway, g of x is going to be actually just 1 minus f of x. All right, and this function, if you think about it, is actually just going to flip the values on the corresponding sets. When x is rational, you get 0, and if it's irrational, you get 1. Now obviously the product of those two functions is going to just be exactly 0. It's just at every point, one of them is going to be 0. So f of x times g of x is equal to 0. And therefore the limit of the product exists everywhere, even though the limits of the individual ones existed nowhere. So the product can be well behaved. I mean, sometimes it's not. It's usually probably not. But the point is, there is an example where you have really bad behaved functions whose product is very nice. All right, so another kind of follow-up. If the limit of f of x exists, I'll just use this backwards e for shorthand, and the limit of the sum exists, does the limit of g exist? Okay. So the idea here is if we set h equal to f plus g, then g is equal to h minus f. So g is actually equal to the difference of two functions whose limits exist, right? Limit of h exists and the limit of f exists. So by the regular limit laws, the limit of g exists, and in fact the limit of g, it must be equal to the limit of h minus the limit of f. Just suppressing all of the subscripts and the variable of the function. Okay. Limit g, right. So yeah, we also get this kind of contrapositive. So if we again assume the limit of f exists, and but that the limit of g does not exist, then the limit of f plus g must not exist. This is just by contrapositive. So when the limit of f plus g did exist, we got the conclusion that the limit of g existed. So under the assumption the limit of f exists, which is common to both, if the limit of g were assumed not to exist, then the limit of f plus g would not exist. So right, for part B, or sorry, or part C, if the limit of f exists and limit of g does not exist, again, this is as x approaches a, then the limit of f plus g, x approaches a, does not exist. Right, to reiterate, by contraposition, if the limit of f plus g exists, then we're in the case of part B, and that automatically implies that the limit of g must exist. Okay. And finally, if the limit of f exists and limit f of x g of x exists, does the limit of g of x exists? Here you might say, well, of course, by the same reasoning as we used for the summation, where, I mean, we just like rewrote g in terms of the sum and f by writing g as h minus f. However, with multiplication, there's a caveat. So if you wanted to do an analogous thing for f of x times g of x, say we want to do h of x equals f of x times g of x. Now if we were to try to isolate g, you run into a bit of a problem. So you have to divide by f. Now, it's not a problem if f is never 0, but it's entirely possible that f could go to 0. So this isn't necessarily going to work. And this is why, for the case of the product, we can actually find a counterexample to this claim, whose counterpart for sums actually happens to be true. Okay, so let me just erase this. So we're going to take f of x equals x, and let's say g of x equals 1 over x, and a equals 0. So then the limit of f exists, that's just 0. Limit of f times g, that exists because f times g is just equal to 1. But the limit of g does not exist as x goes to 0. And the source of the problem is that the function f of x becomes 0 when x is equal to 0. So facts about addition and facts about multiplication are often not interchangeable because of this. And we have to treat them separately. Okay. I think I'm gonna call it a day with that. I didn't get through as many as I wanted to, so I will probably do a part 2 for this chapter. That's okay. It has quite a few problems. It's like something like 42. Yeah, 42 problems. So yeah, I'll probably do one more stream for chapter 5, and then move on to chapter 6 and 7. Chapter 6 only has 17 problems, so that should only take 1. Anyway, we'll get through it eventually, but yeah. So if you were watching, thanks for tuning in. I will obviously leave this up for anyone who wants to check it out later. But yeah,